Okay, so our class on Friday will be online, and I'll email you with the link for that recording as I do. And the only other thing for the class is the homework 12, which is due at 5 o'clock on Friday the 22nd. The two graduate students who are here in the class have their project, but for the undergrads it's just homework 12 is the only remaining assignment. So any questions on the announcements? So we're moving into chapter 14 in the textbook, and I would recommend that if you're not in the habit of following along with the textbook readings, this would be an especially good place to start because a lot of these concepts are a little bit abstract and take more than a single exposure to be able to understand and to be able to explain. You'll have some conceptual questions on the final exam where I'm asking you to define or explain a certain concept, and if you've just heard me explain it the one time, that may not have been enough for you to really absorb what it means and be able to synthesize an answer on your own. So chapter 14 is worth reading. To begin our discussion of flood control, I wanted to point out some information from the book that talks about what is our design standard when it comes to the hydrologic design scale. Balancing the need to build things at an economical price with the desire to have a high level of safety. And so striking the right balance is sometimes a little bit tricky. Knowing how big to build the pipe isn't just a technical decision that's related to the flow rate it has to carry, but it's also a social and economic decision that has to do with your tolerance for risk. And some societies are very comfortable with risk, and they're very understanding when infrastructure is disrupted by flooding, and other societies are less tolerant of risk and less able to bear the costs of interruption and damage to things like roadways and buildings and railways. So one of the bounds that is used for sizing hydrologic infrastructure is estimated limiting value. And this ELV can be thought of in the same way as PMP. If you remember back to probable maximum precipitation, it is just the runoff that you would see in a worst case scenario. So that if PMP is the rainfall side of that understanding, then the ELV would be what is the runoff that's associated with that largest possible storm that you could have. So if the entire air column is saturated with clouds that are about to rain, meaning up to the elevation where the precipitation is frozen and it wouldn't be falling as a liquid, just how much maximum rainfall could you have at a certain spot? That's what the ELV is based on. And so we so far have been talking about design return periods, like a 2-year storm or a 10-year storm or a 100-year storm. If we're really designing critical infrastructure that would risk human life if it fails, we switch over to ELV for design. And so our text suggests that maybe a 500-year storm is about 2/3 of the ELV, about 67% of the maximum that you'd ever see. But of course it's difficult to extrapolate because we don't have measured data up to the worst storm that's ever been seen. We may have some idea of what that ought to be in a few select locations when there's been really impressive meteorological conditions coming together at one spot, but remember that rainfall patterns at one location are different from another. So even if we have seen 100% ELV in Galveston, Texas, we don't necessarily know how that might translate to 100% ELV in Denver, Colorado. So it's tricky. Here is a table that illustrates typical design standards that are used for different types of structures. So a highway culvert that's going on a low traffic roadway out in the countryside may only be designed to convey a flow of between 5 to 10-year storm. But then if you have a culvert that's draining an interstate highway, Maybe you have cars that are moving at a faster rate of speed, more cars in a given day, and the importance of the roadway not being closed has economic significance, and so you'd have a higher return period that you're designing for simply because the stakes are so much higher for a high traffic roadway. So this book goes through different types of both public infrastructure like airfields and so on, but also if you look, it also has different types of dams. And for a lot of these where there's this line, they're suggesting that we use the ELV standard for design rather than a return period storm. So a large dam that has a significant risk of life or maybe a risk of damage to public property, then those would be sized with the estimated living value in mind rather than just a return period. Another one of the interesting figures in our book is this one that helps us to understand cumulative risk. And the idea with cumulative risk is that in this year, 2022, that we're in right now, we're not just at risk of only a 10-year storm or only a 25-year storm. We are at risk of all of those storms, although each of them have different probabilities. Like the 2-year storm, there's a 50% probability that we'll see a 2-year storm this year. But then on top of it, there's also the probability of a 5-year storm, and also the smaller probability of a 10-year storm. And so what this figure kind of illustrates is that cumulative probability. And so the best way for me to explain it to you is, let's consider that we have a 10-year design life, that we want to build something that we expect is going to last for 10 years. And what this is saying is that there's a 90% risk of experiencing a 5-year storm within that 10-year design life. And that may be counterintuitive. So think about a 10-year storm, a 10-year design life, so a period of 10 years, you've got 90% probability that you'll have at least one event that exceeds the limits. So it's a 5-year storm or larger. So it's, remember, not just that 5-year storm, but the cumulative risk of also the 10-year storm, the 20-year storm, and so on. And so in a 10-year design life, maybe the 10-year design life and 10-year return period is even more telling, because you maybe would think that you'd have a 100% chance of seeing a 10-year storm within a 10-year period, and that's simply not true. It's just on average, there is a 10% chance each year, but then when you throw in the other storms that are larger, then the probability is bumped upward from that. So there's a 63% risk of a 10-year storm or larger, and it's not a 50% risk simply because there's also the 10, the 20, the 50, and so on. So that book figure kind of illustrates one of the things that you'll see in the homework assignment, that last homework assignment, where there's a spreadsheet numerical technique where you're going to be integrating the risk. And you're going to be finding out what's the economic value of avoiding flood damage. And so if you are avoiding the 10-year storm, then that also means you're avoiding the 5-year storm and the 2-year storm, all of the storms smaller than that. So there's a numerical technique that takes the size of all the storms either above or smaller than into account. Okay, so just to throw one more example onto the pile. Let's consider a 20-year design life, so a period of 20 years. What if we want to find out what storm size, how big does it have to be so that there's only a 5% risk of one event of that size or larger? So if we go up the 20-year design life and find the 5% risk curve and you go over, it's a 500-year storm. So that may be shocking that within a period that's just as long as 20 years, you've got a 5% risk of having a 200-year storm. So if you think about that, you in 20 years only want a 5% probability that a certain piece of equipment is going to fail, then what that really means is you don't size it for the 20-year storm, you size it for the 500-year storm if you've got a 5% tolerance for failure within that 20-year period. Another point that our book makes in this chapter is just distinguishing between different types of rainfall data. So if we had a 20-year history of rainfall data, so each one of these ticks represents a year, so 1 year, 2 years, 3 years, all the way through 20 years. If we filtered out and found only the top 20 storms, then there would be some years that we wouldn't see any precipitation. And so that's the annual exceedance series, is finding in a 20-year period the top 20 storms, whereas an annual maxima would find the highest single storm in each year. And in the past, some hydrologic data was gathered just looking at the annual maximum of flow through a stream or the annual maximum precipitation at a gauge. And so that if you had two big events in 1 year, you sometimes would lose the view of that other big event. And so the annual exceedance series gives you a more clear and accurate view of the actual risk that you face. And so rather than just looking at the biggest storm for each year, you'd rank the top 20 storms in a 20-year period and use that for estimating your probability and your risk and the intensity, duration, frequency curves. Okay, so natural disasters. I've always felt like here in West Virginia, we're actually pretty fortunate when it comes to natural disasters because we don't have wildfires like they have out in Colorado and Utah, California. So, I mean, occasionally there's a wildfire, but it's never out of control and they're like flying airplanes overhead. We just don't have that. Occasionally you'll maybe feel a little bit of earth movement, but we don't have earthquakes. You know, it's not built into the design codes for buildings, all the seismic restrictions that they have in places like Seattle or Japan or California. So we don't have earthquakes, we don't have fires, we don't have tornadoes really. I mean, a little bit. There was a tornado that came through Ona maybe 10 years ago, and if you looked, you could find a couple of trees that it pulled up, but just the hilliness prevents the winds from getting down into the lower elevations where people typically live. It's just too hilly for a tornado to really do a lot of damage. And what else do we not have here? Tsunamis. We don't have tsunamis. We don't have hurricanes. I mean, it gets rainy when a hurricane hits Florida and then continues here. It gets rainy. Yeah, we don't have tsunamis. Yeah. But we do have flooding. So flooding affects us. It affects other places as well. There was a big hurricane back in 1900 that hit Galveston, Texas. And back then they weren't able to predict when a hurricane was coming. I mean, the only advance warning they had was if there was a boat at sea that noticed the big storm and then radioed it in and someone happened to be listening. Now we can follow its every movement with satellite photos and so on. So they were completely prepared in Galveston, Texas back in 1900. There was a storm surge of 15 feet and the highest point of the ground in Galveston is 8.7 feet. And so the town was basically destroyed, and some of my family members who lived there at the time ended up having to relocate. Everything they owned was destroyed. So flooding is a risk that can cause a lot of social displacement. They ended up building a seawall to prevent that same sea surge from happening again. They put it in a few years later, and there's a similar thing that we did here in Huntington, where after a big flood in 1937, I think, they put in a flood wall that we see now surrounding the city of Huntington. This is an interesting flood that is actually in my memory. I used to live in Utah when I was a kid, and they had a really wet spring at the same time that it warmed up very quickly, and so the snow started melting rapidly. And so there was a creek that normally just kind of meanders through downtown Salt Lake City, and there was so much water in that creek that they had to have it overflow through the main street because there's just nowhere else it could go. So rather than having it destroy buildings and foundations and stuff, they put sandbags down the middle of the road, and you could go watch the river in the middle of downtown Salt Lake City. Of course, flooding in West Virginia is problematic as well. It seems like every year we see photos and hear stories of people whose homes and vehicles have been destroyed. Flooding is a real problem along the Ohio River and the Missouri River because there's just so much land area that drains into both of those waterways that it causes damages to homes, crops, and sometimes the flood walls that have been built fail. That happened back in 2005 in New Orleans, where the flood wall broke and caused considerable damage to the city of New Orleans. So there's just economic damage and disruption to human life that comes from flooding that, if we can prevent, is very valuable. But it's not very visible. And that's the problem with preventing flood damage, is if you spend $10 million to prevent a flood, then you've got nothing to show for it. And I mean the word show literally. You can't take a picture of flood damage that didn't occur. And so it's really unsexy. People hate paying for flood protection because they never see the result of it. It's only the people who have seen flood damage that are directly in favor of flood prevention because they know the disruption that it caused, the expense. And so we're going to talk about both the financial aspects of flood damage and also some of the ways that we can measure the scope of it. And so where does flooding occur? Obviously along where water already is, including coastal areas. One less obvious location is at the mouth of canyons. And so an alluvial fan is more typically seen in places like Arizona, arid mountain locations where streams only flow during high storm events. So that's an alluvial fan, and I've got a diagram in a moment to show you. Also, when the ground dramatically lowers or subsides, then flooding can occur there. In areas influenced by structural measures. This phrase, structural measures, I don't know why they call it structural, but in flood prevention, a structural measure means something that is built to manage the movement of water. So it means a dam or a flood wall or a levee or a dike. And so structural measures, we'll talk about some of the structural measures that are built to prevent flooding and how sometimes they can actually threaten other areas by taking the pressure off of one location and kind of taking all of that water to another. They can increase the risk of flooding at spots that are maybe away from urban areas. There's some technical terms here. The flood plain is what generally adjoins river areas, stream bays, and right now we're standing on a flood plain here in Huntington. The reason why it's flat here and hilly everywhere else is that over many tens of thousands of years, as the Ohio River would flood, it flattened out the ground in this area. So we're on a floodplain here in Huntington. The normal channel shape is where the water flows on a regular basis, and then the floodplain is more flat than the typical channel. And you'll notice if we think of this as maybe here's West Virginia and here's Ohio, of course there's going to be floodplain on either side, but then there is going to be steep areas outside the floodplain. And so maybe, in the West Virginia side, this is Beverly Hills here in Huntington, where it starts to get hilly. They call that Beverly Hills, if you didn't know that. I'm less familiar with what maybe the names of the neighborhoods are on the Ohio side, but you can sometimes see houses up on top of the hills. If you look beyond the floodplain on the Ohio side, there are some developments up there. Here's a photo of an alluvial fan and a diagram that just illustrates that, if you have a series of mountains and there may only typically be a trickle of water going through there, when a heavy spring storm that just dumps a lot of water comes out, then it can start to move sediment. And the fan of it, what that means is the sediment, the rocks, the soil that's been washed out of the mountains once the stream is relatively steep in the mountains, and when it gets to a valley, the slope of the stream flattens out. And as the slope of the stream becomes more flat, the water velocity decreases, and then the sediment that was being moved because of the high velocity of the water settles down. And so it no longer has the suspension velocity to keep it entrained in the water, and so all of that sediment just gets deposited, and so there's like a mound of rocks and soil at the mouth of many canyons. So that's another place where you can have flooding, even in arid areas. Okay, some technical definitions that you're very likely to see on the final exam. I'm very likely to ask you to define the difference between the 100-year floodplain and the 100-year floodway. And so let me explain what that is. So the main channel is where water normally is. Now let's say that there's a 100-year storm and we didn't do any development. So just, before humans came to this area, if there was a 100-year storm, this black line is where it would have normally been. It's called the base flood elevation. So this line would extend to both sides, and they've been a little bit sloppy, unfortunately, on where they put this green line. But the idea is that you could put in some development on either side of the floodplain and only have the water go up by 1 foot. Because I hope it should be obvious that if we fill in some of the sides, then that's going to force the water higher, because you've got less flow area where the water would normally fill in this spot that now has soil on it. That means that during the 100-year storm, the water level is going to be higher than it was before. So in the 100-year floodway, you're not allowed to have any development. And the 100-year floodway is that location that is required to convey the 100-year flow with only a 1 foot increase in the flow depth compared to what it used to be when there was no development. Has anybody driven along a road here in West Virginia where you've seen people putting soil by the creek, like trying to make their yard bigger? There's a guy on the road that I live on who has put so much soil down. I mean, it's totally illegal. I don't know how he got away with it, but he's probably taken his lot from 1 acre to like 10 acres because he's just dumped so much soil in the floodplain to try and give himself a bigger yard and space to store cars and stuff. But it definitely would cause more flooding because there's just less flow area in the cross section of the stream than there used to be. So these technical definitions, what he's done is called encroachment. He has encroached on the channel where water used to go by adding in additional fill. He's forcing the flow to go higher than it was previously. And so the floodway is what should be kept clear to make sure that the water level doesn't rise by more than a foot. And the fringe is that section that can support development with the water level increasing to a foot or less. So the fringe you can have development on, but the floodway shouldn't have development. So in trying to prevent this damage from too much water, the federal government and floodplain managers use a multi-tiered approach. What they try to do is, first of all, reduce the susceptibility of certain areas to flooding. And they may do that by, for example, encouraging commercial developments to have a stormwater detention pond. And so, if you're going to put in a big parking lot that increases impervious area, then requiring by code a pond, like a stormwater drainage pond, would reduce the susceptibility to flooding. So that's one of the measures. Modifying the flood is, we'll look at an example of some measures, is just a way of trying to reduce how deep the water is for a certain return period. And so you may do that by putting in dams. You may do that by putting in levee. There's a lot of different structural measures, as they're called, to modify the shape of the flood damage curve. And then our lowest priority, although it gets the most attention, is helping people when there has been a flood. And that's when, unfortunately, politicians love floods because it makes them look like a hero when they can fly into action and go get a picture taken of them shoveling out mud from somebody's house and signing a bill for millions of dollars of FEMA relief. Politicians actually kind of benefit from flooding because it allows them to look decisive and helpful when it's just so much less attractive to prevent it in the first place. So because of that, there are some national programs that try to encourage responsible development by charging more for flood insurance in dangerous areas and charging less for flood insurance in areas that are less prone to flooding. And so this National Flood Insurance Program is one that subsidizes flood insurance by kind of pooling together people into risk categories. And in a future class, we'll look at the FEMA tool that is used to classify which zone you're in. And there are different zones depending on your elevation and your proximity to streams. And this FEMA website will allow you to put in an address, and then it creates a map that characterizes what's the risk of flooding at that location. The National Flood Insurance Program is supposed to require permits for development in flood hazard areas. And so, for example, that 100-year floodplain that the person out by me is filling in, the county that has homes that are covered by this flood insurance is supposed to have a floodplain manager that kind of inspects, is on the lookout, and enforces these kinds of regulations. It encourages the use of flood-resistant materials that are going to be less prone to mildew damage, and to trying to elevate the lowest floor of finished construction above base flood elevations. And so even if your property is prone to flooding, you'll sometimes see people building up a mound of soil and then building the house on top of this artificially raised foundation for the building. Prohibiting encroachments is the most valuable tool in the tool belt when it comes to preventing the damage from flooding. There are three curves that explain the relationship between rainfall and the dollar value of damage. And these are interrelated, and you should be able to sketch out these curves for different types of structural measures. And so today I'm going to show you a reservoir, for example, a dam and flood control reservoir. And I'm going to show you how it changes these relationships. And so let me talk through what they are. First of all is the relationship between exceedance frequency and discharge. So a hydrologic model like HEC1 or TR55 or the rational method, that's where you put in a storm return period, like a 10-year storm, and you get a Q, a flow rate out of that. And so at a given location, there's just a curve. It may be a straight line, depending on if we made it like logarithmic, but there is some relationship between increasing size storms and increasing flow rate. So this one, I hope by now, is pretty straightforward and natural. The idea that you could get data, probabilistic data, that says how often a certain size storm comes around, and from that, with modeling, predict the flow rate, the Q. Okay, this curve, stage versus discharge, is a hydraulic analysis. This first one was hydrology. This next one is hydraulics. And what it says is for a certain flow rate and a channel, you need to be able to predict what is the depth. So for any of you who are in 331 this semester, can you think of a model that predicts the flow depth when you know the flow rate? An equation maybe? where with a given Q and knowing what the channel looks like, it predicts the depth Y. Manning's equation is an example of that. If you have steady uniform flow, you could use Manning's to create a curve of different discharges and different depths. And so this is a hydraulic analysis that defines this curve. And you'll notice that they've specifically illustrated this as being nonlinear. Because if it was like a trapezoidal channel, then even if your discharge is getting higher and higher, because the channel is getting wider, that doesn't necessarily mean that the stage is increasing at the same rate. And especially if it's a floodplain. Because if it's a floodplain, you may have an enormous area that becomes submerged with just a tiny increase in stage elevation. And so you could convey a huge discharge with just a slight increase in stage. But that hydraulic analysis is what defines this curve. And the last one is maybe an economic analysis. The relationship between if the water gets to a certain depth, how much money is that going to cost to repair? So to do that, you'd send someone out maybe with an elevation map, and you're identifying which structures are at what elevation, and then how much are they worth. And if the water gets to 1 foot of depth at a certain structure, you'd have to have maybe some understanding of construction and repair due to flood damage. But basically, you have some curve that says, depending on how high the water gets at a certain location, how much damage there's going to be. And so what this is saying is the water can be up to a certain depth and there's no damage. So that's like normal flow through the main channel. But then when the water starts to spill out of the main channel, then any further increases of the stage, meaning depth, is what begins to cause damage. So if we wanted to do an analysis of this building that we're in, we could say if the water got up to 2 feet, probably we're going to have to rewire the building because our electrical sockets are submerged. We'd have to get new carpet, new baseboards. We maybe wouldn't have to replace the chairs because the cloth part of the chair maybe would or wouldn't be submerged at a certain elevation. But just the deeper you go, the more that damage is going to be. So by considering these different flood control alternatives, our objective is to reduce damage. We don't necessarily care so much about reducing discharge or reducing depth just for their own sake, although reducing both of those would reduce the damage. Because think of it, if you have less Q, then you will have less Y. So less flow rate means less depth, naturally. And less depth is what means less damage. So we want to reduce the consequences of flooding, and the quantifiable way for us to measure those consequences is dollars. There are other non-economic consequences or consequences that are hard to monetize, like inconvenience and disappointment. Someone's family photo album or the family Bible. And maybe it doesn't have an economic value, but it has a lot of sentimental value. So there's non-economic costs as well. Let me show you an example of a reservoir, Tygart Lake, which I've never actually seen before. Has anybody been to Tygart Lake in Grafton, West Virginia? Anybody know where that is? I don't. I think it's maybe up by Pittsburgh. But it was a project that was authorized in 1935. So it was probably built and finished sometimes in the 1940s. But according to the Army Corps of Engineers, there was a storm back in 1985 where in that one storm, having this reservoir prevented about $200 million of damage. And they're able to calculate that by estimating, if that flow had been released, and knowing downstream what are all of the structures that would have been submerged if that flow had been released. So over the years, they estimate that the flood damage prevented is $1.2 billion, and this dam costs $18.5 million to construct. Now, in a sense, they're kind of exaggerating, because probably a lot of the buildings that are protected by this wouldn't have been built if the dam wasn't there. And so it's kind of a chicken and the egg thing. They built the dam so that the area downstream that was already built would be protected. But then what it also did is it enabled development that would have been stunted if people were worried about the flood control risk. And so it's definitely valuable, but it's not prevented $1.2 billion worth of things that were there before the project was constructed. So what they had to do when they decided, should we spend $18.5 million, is they had to think, what are all of the benefits, both protection of existing property and protection of future property that may be put into place if you've got flood control in place alongside the downstream river. So it's just an illustration of the scale of savings that you could see. The storage of the reservoir behind the dam, it says that they have the ability to store the equivalent of 4.56 inches of precipitation of the 1,100 square mile drainage area. So that's a lot of water it can hold. I assume that's if it was empty, so it's probably never all the way empty. So its absolute capacity to suppress flooding maybe is less than this would suggest. Okay. So I suggest that you sketch out these curve relationships and think about like what it means. So for example, the way that a flood control reservoir prevents damage, it's not affecting the stage versus damage curve. And so when you build a reservoir, you're not going to people's buildings and flood-proofing them, which is what it would take to affect this curve. You know, stage versus damage, you're talking about like lifting up a building or using flood-proof materials that can get wet and aren't ruined. So a reservoir doesn't do that, and a reservoir also doesn't change the channel characteristics, which is this discharge versus depth curve. What it does is it changes how much water is going to be in the channel for a certain return period. So exceedance frequency is for a certain storm size, how much flow is going to be in the river. And so the black line is the original relationship, and what the reservoir does is produce this dashed line. And so for most of the storms, like the bigger ones, for a certain return exceedance frequency, let's say for a 50-year storm, originally we would have a certain flow rate for a 50-year storm in the stream, but what having this reservoir does is it means that there's going to be a lower flow rate going through the channel because it's kind of acting as a shock absorber. You know, the water goes into the reservoir. If we go back to this picture, when they've got a here it is. When they've got a flood, it fills up the dam and it's released out at a constant rate from the dam, whereas instead of just washing through immediately. And so here, that's why most of the curve is below the solid line. What they're expressing with this curve being above the solid line for the lower exceedance frequencies is just that water is going out of the dam even when it isn't stormy. So this you can think of as like the base flow. So the discharge, there's always some water coming out of the reservoir, but then when you have a big storm, you're having a lower discharge for a certain exceedance frequency. And so what then that means is that there's going to be less damage because you had less discharge. The disadvantages of reservoirs, besides the fact that they're expensive, is that they can trap sediment. So water that ordinarily would be moving at a certain flow rate and carrying sediment, that sediment can be deposited in a reservoir, and then the water that comes out of the reservoir is like hungry for sediment. Since it's not already carrying sediment or it doesn't have turbidity, there can be erosion of the channel downstream that maybe wouldn't have occurred in the absence of the reservoir. And that's a really long, complicated topic. There are plenty of reservoirs and dams out in the western United States especially that they're starting to tear down because they've noticed that there are some environmental disadvantages. Even if there are advantages of flood control and producing electricity, dams and reservoirs aren't so good at allowing fish habitat through. They're also bad at sediment being trapped that otherwise should be left to go downstream. And that's part of why, I don't know if you've heard that New Orleans is sinking and like the Mississippi River Delta is starting to shrink, is because all of the sediment that should be going towards New Orleans to keep it in equilibrium is being scoured by the ocean and moved downstream by the Mississippi River, and there's lots of sediment that would have made its way downstream that's been trapped by all of the reservoirs that are upstream. The other issue that our book talks about is just how this stage versus damage relationship can be changed if people build more because now they know that there's flood control. So you may actually have more damage some years later simply because there's the perception of safety. And so maybe you had 10 buildings along a stream, but now when you've got 100 buildings alongside the stream, even if it's flooding less often, there's just more valuable property there, so the net dollar cost damage could be higher. Okay, our book talks about some locations where reservoirs may be suitable, like if you're trying to protect a large area, you want a lot of protection rather than just partial protection against flooding, a variety of property types. These different categories of suitability, each type of structural measure has its own subset of advantages versus disadvantages. Some of them require a lot of land area, like a reservoir does. Other structural measures don't require any additional land area, like floodproofing, for example. But for the case of a reservoir, the main things that would make it suitable is if you've got the budget for it, meaning that there's some justification for the high degree of protection because it's so costly. The land area being available. Sometimes they'll put in underground reservoirs for flood protection, like in Tokyo where real estate is very, very expensive. They have large underground vaults that stormwater goes to during rainy days, and then they have to pump it out of the vaults with large turbine engines. Now, just to talk about one more structural measure today, let's take a look at a video that illustrates a diversion. I'm going to mute this. Okay, so let's say that we've got a city that is on either side of a river that is prone to flooding. And historically, there have been floods that here in red you can see what are the areas that have experienced flood damage before. And so if they don't have some place that they could put a reservoir, an alternate approach for providing protection would be to put in a bypass. And the bypass says, instead of allowing the water to meander only through this part of the channel, let's build a bypass that some of the water would be directed here to the left and would go around this valuable, expensive urban property. And so the way it works is that they would build the bypass at a higher elevation than the main channel, so that the water would only go into the bypass if the water level is rising above a certain elevation. So you'll see what the diversion structure looks like. It's similar to a spillway. Let me skip ahead a bit. So as the water level rises, then some of the water would go into this artificial bypass that goes around the town. So you can kind of get a sense for the fact that, maybe if you can accommodate the 100-year storm through the main channel without flooding the adjacent developed areas, then anything above that you'd hope to put through the bypass. So the way that a diversion protects and avoids damage is by changing the exceedance frequency versus discharge curve. And so the original relationship is the solid line, and look at how it suggests the diversion protects things, is that there is going to be a certain amount of exceedance frequency that causes no additional discharge through the main channel. So once you get up to that point there, the water is being redirected through the bypass, then any additional flow isn't any additional rainfall. Like as the storm gets bigger, it's not increasing the discharge into the main channel. But once you get beyond a certain point, you still have the discharge going up, and maybe it's going up higher than it would have before. The steepness of this line is just suggesting that if you put in the diversion, then you may have additional development along the floodplain that reduces the channel's capacity to carry more flow than pre-development. But it's this horizontal component of the line where the protection is provided. You're not having any increase in discharge, although the exceedance frequency does go up. All right, we're out of time for today, so we'll continue talking about these structural measures for flood control. But later today, I'm going to post the assignment for homework 12, so that if you want to get an early look at that, you're welcome to get started, but it won't be due until Friday of next week. This Friday's class is online, so I'll see you face-to-face on Monday, and I'll email you the link for Friday's lecture.